Hello, everybody. Are we all set? Can the secretary confirm that we're all set?
Yes, we are.
Is Cole there?
Yes, I am.
Okay, then we can start. So, dames en heren, ladies and gentlemen, geachte collega's, dear colleagues, I hereby formally open this session and I welcome you all to the public defense of Mr. Cole Johnston. Mr. Cole Johnston has presented to the faculty his PhD thesis on the topic Interior Modeling of Massive Stars in Multiple Systems, in partial fulfillment of the requirements for the degree of PhD in Science, Astronomy and Astrophysics. He shall now publicly defend his PhD thesis. Mr. Cole Johnston, you are invited to give a presentation of about 45 minutes about your work. Afterwards, the examination committee will ask questions and discuss your work with you. I now give the floor to Mr. Cole Johnston.
Hello, everyone. I'm going to share my screen, application window. All right, I hope everyone can see this. All right, so, and with that, I'll say thank you for everyone for joining in and tuning into this online defense. Today, I'll be speaking to you about my work and on the interior modeling of massive stars in multiple systems. And we're just going to hop right along into it. So stars form a very interesting intersection in the field of astronomy because stars are the building blocks of galaxies. They're the chemical factories that produce all the heavy elements that will eventually form planets and potentially life like us. They're the progenitors of supernovae and the hosts to exoplanets. So in this way, we can see that many different fields of astronomy end up relying on theory of stellar structure and evolution to be robust and accurate in its predictions. But to be able to say anything at all about stars, we first need a way of categorizing or classifying them. So to do that, I would like you all to imagine that you take, I don't know if you can see my mouse, if you can take all the stars here, and first we're going to sort them according to color, because color is indicative of a star's temperature. And then second, we're going to sort them by brightness, and we will arrive at a diagram such as this, which is known as a Hertzsprung-Russell diagram. And we can see that the stars form these nice patterns and sequences on this diagram, with our sun placed here, stars cooler than our sun to the right, stars warmer or hotter than our sun to the left, bluewards. And this diagram is very helpful for many reasons, but also because it encodes a bit of stellar evolution in it as well. And right along this very conveniently named main sequence, stars will spend about 90% of their life slowly burning or fusing hydrogen into helium in their cores. Now, eventually a star will run out of helium in its core, and when it does that, it will evolve off the main sequence. It'll run out of hydrogen in its core, and it will turn off the main sequence and evolve upwards and right, generally speaking, in this diagram. But what's important to know at this point is that the characteristics of the remainder of a star's life are in fact dictated by the physics that occur in the deep stellar interior while it's on the main sequence. And this kind of gives us the incentive to try to sort out what's happening on the main sequence. And then this diagram gives us our first ability to actually start to scrutinize the theory of stellar structure and evolution, because if we can place the observations of real stars on this diagram, that will then allow us to test our theories by comparing them, by matching the models to the observations. In this thesis, we're going to focus on the impact of the impact of chemical mixing in intermediate and high mass stars. And that means stars that have at least 1.2 times the mass of the sun at birth or more. And then, so unless otherwise specified, for the rest of this talk, I'll be referring to these stars here, denoted here as they are on the main sequence. And another thing too that's important to note is that these stars all have a well-developed convective core while they're on the main sequence. And just briefly before I move on, I'd like to address the point that for the purposes of this discussion, you'll see luminosity, or L, on the y-axis of a lot of plots, and that is, for all intents and purposes, the same as brightness. So stellar modeling in its rawest form is done by comparing model predictions. So the predictions of a stellar model calculated according to some theory, and comparing them against data that we've taken of some star or stars, probably through a telescope. And this comparison is at the heart of our work. And what we're really asking here is, how likely is it that our model represents the data that we have? And although getting the data certainly is no straightforward task, we're going to take it for granted and instead focus on the models themselves. So a stellar model consists of, at its minimum, 4 main ingredients. First, we need to know the mass of the stellar model that we're going to calculate. And then we need to know the chemical composition of the model that we're going to calculate. And the chemical composition is comprised of the hydrogen mass fraction, denoted by X, the helium mass fraction, denoted by Y, and the metals mass fraction, denoted by Z. And then we can take these ingredients, toss them into some stellar evolution code, such as MESA, which is the one that we used for this work. And then you'll get a stellar evolution model. And as that model evolves in time, you'll then get this evolutionary track. So when a star is first born, it will be here on what's known as the zero-age main sequence, or the ZAMS. And this is when it starts burning hydrogen in its core. And it's going to continue happily burning hydrogen along until eventually it runs out of hydrogen. And this is what's known as the terminal age main sequence, or the TAMS. And then at which point this will zoom off to the right in the diagram, like I had mentioned previously. But now we have some idea of how a star evolves within this HR diagram. But now we have to think, all right, how are we going to get the information to put the stars on this diagram to make these comparisons? And in this work, we're going to be using the information gathered from the analysis of multiple systems and through astroseismology. So the most simple type of multiple system that we have is a binary system. And a binary consists of 2 components, so 2 stars, a primary and a secondary, which are thought to be born at the same time from the same cloud of material. And then this allows us to assume that these 2 stars have the same age and the same initial chemical composition. And then if we observe the composite light from the 2 stars, we can determine the individual temperatures of the stars, their individual surface gravities. And from the relative Doppler motion of the 2 stars, we can then determine the ratio of their masses. If we're lucky enough, however, that the stars are oriented in a way that they appear to cross each other's path with respect to us, as indicated by this diagram here, the stars will undergo eclipses. And if we can model these eclipses, then we can determine the actual absolute masses and radii of the star instead of just their ratios. And we can do this down to a very high precision of about 1% or better in many cases. And these masses obtained through this method are referred to as dynamical masses. So now we're going to take a look at a real-world example of this. These are the primary and secondary component for the binary V380 Cygni, which is an intermediate mass binary, eclipsing binary, where we were able to determine the dynamical masses of the components of this system to, again, 1%. But then if you go ahead and you calculate stellar evolution tracks at those masses for the primary and the secondary, denoted by the solid black and gray lines here, you notice that the evolutionary tracks for models of that mass don't at all match the observations. And that's a bit of a problem. And now one thing that we can do is we can ask the question, what happens if we just allow, what kind of mass do we need for a stellar evolution model such that its evolutionary path or its evolutionary track passes through the observed spectroscopic temperature and surface gravity? And then this is what's referred to as the evolutionary mass. And the difference between these two masses is something that's known as the mass discrepancy. Now, this is a problem that's been known in literature for quite a long time, and it's kind of pointing at the idea that our theory or our models are in fact missing something. And one of the proposed fixes or remedies to this has been the inclusion of enhanced internal chemical mixing in our models. So just a schematic example of that, in our star, in our intermediate mass stars, we have they have a convective core and a radiative envelope, but we want to consider two different areas in the star where chemical mixing can happen. So we have this convective boundary mixing region here, or the CBM region, shown in yellow. We just have some mechanism that's active that induces turbulent or some sort of mixing of the material there. And then in the radiative envelope, we can consider another mechanism or several mechanisms acting individually or in concert. And we're going to refer to this as radiative envelope mixing. Now, when you add all these together, all these mixing contributions together, they form a chemical mixing profile throughout the star, which really functions as a chemical transport network within the star. And why that's important is that it drags fresh hydrogen from the envelope and pulls it right down into the core so that it too can be included in the hydrogen burning of the hydrogen burning in the core. And this has some major and profound impacts on the course of stellar evolution. First of all, it pulls this hydrogen in and it effectively gives new fuel to the core so the star will be able to live longer on the main sequence. And second, it will enhance the mass of the core quite significantly. And an example of that is shown in this schematic here, where we have the mixing efficiency in a given region as a function of the fractional mass, where the left-hand side of this plot is the core, the right-hand side is the envelope. And we have two models here, one that's not hatched and the other which is hatched. The red regions are denote the convective core in our models. The yellow regions denote the convective boundary mixing region, and the blue the envelope mixing region. And these two profiles belong both to three solar mass stellar models that have been evolved to the same fraction of their evolution. The only difference in the two models is that one has had a small amount of internal mixing, whereas the other has had a much more enhanced amount of internal mixing. And as we can see, the model with more internal mixing, the hatched model, actually extends to a much larger point. A much larger fractional mass of the star. And actually, this is the model with the enhanced mixing has a core that's 36% more massive than the other model. And this also translates into more global differences in the stellar evolution that can be observed in the Hertzsprung-Russell diagram. So we return to the example that we saw before. These are all tracks for three solar mass models that just have different amounts of mixing. Down here is still, this point down here is still the zero-age main sequence. And then the solid black track is the one that we saw earlier. The dashed and dotted black tracks, however, are models that have different amounts of internal mixing, increased amounts of internal mixing. And we can see that not only does the main sequence appear to be longer, but that the point where it runs out of hydrogen in each model is actually at a very different point. Furthermore, the age difference between the minimum mixing model and the maximum mixing model is about 30% different at the TAMS point in their evolution. So as we can see, this has a pretty large effect on the evolution of stars, and this is exactly what has been used to try to explain some of the observations that are seen in terms of this mass discrepancy that we saw earlier. So now the models that do have this enhanced internal mixing can also reproduce the observations of the primary. And now, as I was saying, this is not a new problem. This has been thoroughly investigated since it was first characterized in 1992 with theoretical considerations for it going back into the 70s. And although there is a tremendous bit of literature dedicated to addressing this issue, there's really no clear consensus as to how to solve it. And a lot of that comes down to methodological differences between the different studies. So now I want to switch gears a little bit and then talk about the other methodology that we use to get information about stars, and that is astroseismology. And astroseismology is a study of stellar interiors through the analysis of stellar pulsations. And this has a very intuitive real-world analog. So where seismologists here on the Earth use earthquakes to study our planet's interior, astroseismology uses stellar oscillations or starquakes to study stellar interiors. And then, so very much in the same way that the size, the shape, and the composition of a bell determines how the bell rings, the frequency with which the bell rings, the size, the shape, and the composition of a star will determine how that star oscillates. So while seismologists here on Earth use seismographs to study, to track earthquakes, we astroseismologists study the variation in brightness over time of stars, where an example of a light curve here, you can see several the periodic brightenings and dimmings of a star, and these are caused by pulsations. And generally speaking, pulsations can be categorized into two classes. The first being P modes, which are pressure waves or sound waves that propagate throughout the stellar interior. And although these are very important for investigating the envelope of stars, we're more interested in G modes, which are buoyancy waves that propagate more in the deep interior of stars. And an analogy for a G mode is going to be, as opposed to a sound wave with a P mode, you have G modes are alike to surface waves that travel along the surface of a pond. And now, as I was saying, these G modes are very sensitive in particular to the near core regions of stars. So they're going to be sensitive to any mixing process that is happening next to the core. And that's why we want to utilize them. Additionally, G modes, as it just so happens, occur in many of the classes of stars on the main sequence that are just in this region that we want to investigate. And now this is the only formula in the presentation, I promise. While many astroseismic investigations study the individual periods of stellar pulsations, we want to use a more global astroseismic diagnostic, and that comes in the form of the asymptotic period spacing value here. And this is going to be sensitive to the conditions of the near core through this quantity here, the Brunt by Sala frequency. So there have also been numerous astroseismic studies that have tried to pin down the efficiency of internal mixing in G-mode pulsating stars. And really what we're finding from these studies is that there's a range of mixing efficiencies that are required to adequately explain the astroseismic observations. And not only that, but they seem to indicate that we need a little bit of radiative envelope mixing as well. And we're going to use these results to motivate our methodology in a little bit. But now I want to introduce the idea of pulsating binaries. And by this, I mean a binary system that has at least one pulsating component in it. And again, there have been several studies that have tried they've successfully incorporated binary information and astroseismic information in their analysis. But more often than not, these studies end up doing their seismic analysis and then using the binary information as an a posteriori sanity check for their models or consistency check. But so in summary, what we want to say is that astroseismology says that there's a range of mixing efficiencies that are required to explain observations, and that envelope mixing in some form seems to be needed. The binary studies and the conditions from binarity give us very precise masses and radii, and we get the assumption of equal ages and the same initial chemical compositions. And then past studies have shown that, past binary studies in particular have shown mixed results on convective boundary mixing. And the reason I'm summarizing this is because this is going to inform our methodology. And then so what we want to do is develop this new a more pragmatic methodology when it comes to the modeling of multiple systems, where we're going to simultaneously apply binary and seismic information when possible, just up front in the modeling. We know that mixing is important, as we've just seen, but from a few studies, we know that the different mechanisms themselves might not be important so much as the fact that mixing is there in some form. And we know that from astroseismology, there is a range of mixing efficiencies that we need to take into account. And then so we're going to ask the question, or we're going to look at this in a new way, and we're going to try to constrain the impact of internal mixing on core masses, because we know that internal mixing impacts core masses. So this is the characteristic of stars that we're going to try to look at in these cases, as opposed to trying to calibrate the efficiency of one or several given mixing mechanisms. And so to that end, although there may be any number of actual mixing, of other mixing mechanisms active within a star, we're going to restrict ourselves to one representative mixing mechanism in either, or in both the convective boundary mixing region and in the radiative envelope mixing region. So in our stellar models, we're going to fix the efficiency of convective mixing just for simplicity. And then in the case of overshooting, or sorry, in the case of convective boundary mixing, we're going to use an overshooting prescription as representative of all the mixing that is taking place in the convective boundary mixing region. And overshooting in this study takes the form of an exponentially decreasing function that we can see here, where it's most efficient next to the core, and then the further away from the core it gets, the less efficient it becomes. The slope of this decrease, or how quickly it decreases in efficiency, is determined by a free parameter that is input by the user in a stellar model, and this is exactly what we want to end up calibrating. The radiative envelope mixing is going to be represented by the chemical mixing profile that is induced by internal gravity waves, and that can be seen here in blue. We can see that this profile increases inversely with the density, so it will increase as we move outward radially. Now, internal gravity waves are traveling waves that are excited at the boundary of the convective core and the radiative envelope. And what ends up happening is that you have the turbulent motions of the convective core shown here in this hydrodynamical simulation. And as these convective plumes end up bumping up against the boundary, they'll excite these waves that travel outwards. And then these are going to induce the chemical mixing that we showed in that profile. And now that brings us to the consideration of what goes into our stellar model. Just for simplicity's sake, we're going to assume that the chemical composition is fixed, largely because we're working with multiple systems, so we can make the safe assumption that the two components, or the multiple components in this system, all have the same metallicity. And now we're just going to want to look at the mass of the star and then try to calibrate, if possible, the mixing efficiencies for the convective boundary mixing region and then the radiative envelope mixing region. And that brings me to the first step in our methodology, introducing the idea of isochrone clouds. So an isochrone is simply a line that connects all the points of one age in a grid of stellar models. So over here we have a grid of stellar models in gray, and then this black line is a 50 million year isochrone. So we just go to the point in the first track and say, where along this track is the model 50 million years old? Here, next mass track, so on and so forth. And then we get this nice black isochrone here. However, with the inclusion of enhanced internal mixing in our models, we have a bit of a complication. And that's because if you build an isochrone, a 50 million year isochrone, again, from a set of models or a grid of models that have one mixing efficiency, one small amount of internal mixing, as denoted by the solid gray tracks here, we'll get one isochrone. If we want to calculate an isochrone of the same age, so still 50 million years, but from a grid of tracks that have enhanced internal mixing in them, denoted by the dashed gray tracks here, we get an entirely different function in the parameter space, despite the fact that this isochrone is calculated again for 50 million years. And then you can see that if you were to try to fit your observations to either one of these isochrones, you'll end up biasing your results. And this is because you're enforcing that the components of your multiple system have to have the same amount of internal mixing, which may not necessarily be the case. And then that brings us to the idea of isochrone clouds. So instead of considering either of the limiting isochrones, we want to consider all the points within that are bounded by these two isochrones, and the mixing efficiencies that went into building the limiting isochrones are informed by the astroseismic results that we had earlier. So now that we have our isochrone clouds, you might wonder, well, how do we fit isochrone clouds to our observations? And first, we're going to consider the 1 sigma uncertainties on the spectroscopic temperature and surface gravity for our primary and secondary stars, shown here. And we're going to only count an isochrone cloud as valid if at least one point in the isochrone cloud satisfies both uncertainty boxes. So we can see in this case that this isochrone cloud is not considered valid for this binary. Now, if we go to an older isochrone cloud, we see that we do have one point that satisfies the uncertainty boxes for the primary star, and we still have a number of them that satisfy the uncertainty box for the secondary star. And then we're going to count a valid model as the combination of all points in the primary uncertainty box and all points in the secondary uncertainty box. And then we're just going to compare all of these models to the observations and pick our best model from there. And this brings us to the first application of this methodology where we're going to combine astroseismic information and binary information simultaneously, as we said before. And we're going to do this on a sample of double-line spectroscopic binaries that were observed by the nominal Kepler mission. And unfortunately, they're not eclipsing binaries. So we can't get the actual masses and radii of the star, but we can get the mass ratio, the temperatures of these two stars, as well as the assumption that the stars are of the same age and initial chemical composition. And then we're going to use the astroseismic information from these stars in the form of that asymptotic period spacing value that I showed earlier. And then we're gonna treat this as two cases because we want to see how the application of the binary information kind of modifies our solution space. So the first one we're going to do is we're going to pretend the primary component, which is the pulsating star in this binary. We're going to consider that this is just a single star. We're going to make pretend, and we're only going to care about the effective temperature and the surface gravity of the primary in addition to this asymptotic period spacing value. And then we're going to apply our isochrone cloud methodology to the modeling, and we're going to model both components simultaneously with the inclusion of the mass ratio and the equal age constraints. And then just the only example of this that we're going to look at is for KIC 4930889, because astronomers are great at coming up with names for stars. And this is a G-mode pulsating B star. And what we can see in this case, in the evaluation of this star as if we pretend that it's a single star, we're going to want to try to deduce the age. We're going to try to deduce the efficiency of the near core mixing, and we're going to try to deduce the mass of this star. And how good of a match our model is to the observations is determined by the color, as shown here in these correlation plots, where the darker the color, the better the match. And what we see is that we don't have just a single best match, but we kind of have a region of best matching models, and that's what's known as a degeneracy. And this is a very common problem in astroseismic modeling. And this degeneracy is just something that we have to deal with. But what's more important is that we see that there's no reduction in the parameter space. So we get returned basically our entire input grid as potentially valid solution. We couldn't make any constraining remarks at all. Although the best age for this star is something like 85 million years, the uncertainty range goes from 0 to 2 billion years, and then the mass goes anywhere from 2.5 to 9 solar masses. So we couldn't make any constraints at all. But when we end up applying the isochrone cloud methodology, just by nature of the methodology and enforcing the equal age constraints, we find that we can make very strict cuts in which ages are valid for the components of our system, or for this star in particular, which then directly corresponds to reduction in the valid mass range of our models. So we can see that the mass range has been restricted quite significantly, the age range as well, and furthermore, we see that the correlations, these degenerate regions, are pretty much mitigated in these cases. We have a more singular solution space, and that's great. However, we still can't say anything about the efficiency of the mixing near the core. That's an important result. Now we're just going to look at this in tabulated form very quickly, because I think it makes a great point that just by applying the isochrone cloud, just by applying the isochrone cloud methodology to our modeling, we have a 94% reduction in the uncertainty on the age and a 46% reduction in the uncertainty on the mass of the primary component. And that's I'd say that's a pretty good reduction in uncertainties. And the more striking thing in this comparison is that the convective core mass of our models, of our best models in the two cases, seems to be the same. And that's because the seismic diagnostic is very strong, and it constrains the mass of the convective core quite a bit. And then we see that the age and the mass of the two solutions change quite a lot. And that's because of these degeneracies that I was speaking of before. But the important thing to take away from this is that the seismic information in our methodology gives us information on the core mass, and the binary information greatly reduces the modeling uncertainties that we have. But really, what's important here is that the core mass is key. And that's something that we're going to come back to again in the next case, where we're looking at eclipsing binaries. So we're going to take a look at some eclipsing binaries, or just one in this case. We've applied this to two eclipsing binaries, but I'm only going to show you the results of one. And this is the case for CW SEP. And what we went and did is we modeled the eclipses in this system, and then that returned to us very precise estimates on the masses and radii, as you can see here. And then we also have the spectroscopic uncertainties for the log G and the effective temperature shown here. And then we're going to apply our isochrone cloud methodology, as we discussed before, where the gray regions in this plot here correspond to the solution space that is allowed by our isochrone cloud methodology according to these parameters. And the blue regions correspond to all the models that could possibly be allowed by by considering models that have a mass within the uncertainty estimates for the dynamical masses of the two components. For the primary is these two patches, and the secondary is for these two patches. And what we immediately notice is that there's a little bit of contention between the solution for the secondary star, where the x-axis is actually a proxy for the age of the star, with younger models to the left, older models to the right. And we see that we can actually, the isochrone cloud methodology restricts the mass of the convective core to quite a narrow range. And then compared to other models at this age, or other models at this age, we see that to be considered at the same age as the primary, the secondary is going to have a more massive core. And this is again shown in tabulated results for both components, where we see that we can in fact infer what the core mass is for these two models, but we cannot in any way, shape, or form constrain the amount of near core mixing. And again, this is just something that we're finding again that has been shown in literature quite a lot. The efficiency of the mixing can't really be constrained in the case of binary modeling. But what we do now that we know that we can infer the core masses of these stars as has shown by the past two examples, is we want to expand this to a much larger sample of stars indicated here. So we have 10 binary systems with 20 components that have their masses, their dynamical masses in radii determined to a precision of 1% or better. And we want to use these to investigate this mass discrepancy that we introduced earlier on. And then so what we're going to do is we're going to pretend all stars are single stars, and we're going to consider 4 solutions that correspond to 2 different cases. The first case is we're going to fit our models to grids. So we're going to fit our observations with models that come from grids with no mixing. Second, we're going to do the same thing but with mixing. And just to show you a familiar example of what this means, in the first case, solution 1 is going to be the dynamical mass, a model with the dynamical mass that has been computed, at the dynamical mass that was determined through eclipse modeling. And the second solution is where we're going to let the mass go free and see how much more massive does the model need to be in order to match the observations. And then we find the results here, and this is a quantification of that mass discrepancy over quite a large range of not only masses but evolutionary stages, where this is a proxy for evolutionary stage down here. But the important thing here is not that we recover this because this was known, but that we show that this corresponds rather to a discrepancy in the convective core masses of these models. And that's important because now we're seeing that the classical mass discrepancy is, or can be viewed as, a core mass discrepancy. So now we're going to look at the second case where we have the solutions where we allow for internal mixing. And we're going to, again, first we're going to calculate an evolutionary track, or we're going to calculate models that are fixed at the dynamical masses that were determined from the eclipse modeling for all the stars, but we're going to allow for internal mixing. And then the fourth solution, or the other solution in this case, is going to be where we allow for the mass to be free as well as the internal mixing to be free. And what we find in this case is that across the board, by doing this, and when we take the difference between the 2 solutions, the mass discrepancy is in fact reduced. It's, like I said, just reduced across the board. And there's also a few select systems here where the mass discrepancy disappears entirely. And really what this is saying is that enhanced mixing reduces, obviously it reduces this core discrepancy, this convective core mass discrepancy, because it produces more massive cores. And the takeaway from this is that core mass is really the thing that ends up determining your position in the Hertzsprung-Russell diagram in these cases. And finally, I'd like to take a look at the example of young massive clusters. Now, this isn't something that we set out to do, that we set out aiming to do at the beginning of the thesis, but that we came across at some point and realized that maybe we could make some inferences here. So in general, a cluster can be considered just a very scaled up version of a binary system. So instead of 2 components, we have up to millions of components in one cluster. So millions of stars, that at least in the case of young massive clusters, and this isn't necessarily the case for globular clusters, but here it's still thought that that all the stars in this cluster are formed at the same time from the same cloud, so that they all have the same age and same chemical composition. And instead of trying to go through and determine the temperature and the surface gravity, or the masses for any of the individual components, or all of the individual components in a cluster, what we're going to do is just measure the brightness and the color of all the components in one of these clusters, and then plot it in the observational counterpart of the Hertzsprung-Russell diagram, where this is known as the color magnitude diagram. And just in the way that we could fit isochrones or isochrone clouds to the 2 components of a binary, in this case, we're going to fit our isochrone clouds to this entire population simultaneously. So the reason that we want to look at these young massive clusters is this phenomenon known as the extended main sequence turnoff, where, generally speaking, if you have a cluster that is comprised of a single population of stars, you would expect that the most massive star in your cluster is going to be directly related to how old that cluster is. Since the lifetime of a star is related to how massive that star is, how old the cluster is determines the most massive star that can still be alive, or that can still be on the main sequence, not alive, at that age. And then so what you would expect is that the models will at these most massive stars, they'll just start peeling off to the right in some very nice uniform sequence. But what is in fact observed instead is that this isn't a single function, but it's a spread. You have this spread of models, and it looks a bit messy. And usually this is explained through the effects of rotation or near critical rotation in stars as they are randomly oriented throughout your cluster. But then we started thinking, how much can an enhanced core mass, or a population with a spread of enhanced core masses, explain this phenomenon? And we were quite happy to see that very naturally our isochrone clouds kind of explain this observed phenomenon, where for a younger isochrone cloud you see that it's still a bit tight in the spread here. That's because this is a young age, and the mixing hasn't had much time to take effect. But what you eventually see as we go to 150 megayear isochrone cloud is that the models with the most, despite the fact that all of these stars are the same age, the models with the most internal mixing have been kept relatively young, or they appear to be in an earlier part of their evolution compared to those that have less internal mixing. And then you see the same going for even older. And this is driven by the distribution of the fractional core masses of your models, where the black here corresponds to the fractional core mass for all the different models within all the different stellar models within this isochrone cloud. And we see as we get older, the distribution shifts and gets a little bit broader. And that's this change in fractional core mass is what drives this spread in our isochrone clouds. So we apply this to two clusters, the first of which is a cluster in Large Magellanic Cloud, NGC 1850. And we're going to fit, or what we ended up doing was fitting all the points that you see here that are colored to our isochrone clouds. And the color here is indicative of the fractional core mass of the best matching model within the isochrone cloud. And what we found, sorry, I should have said that we fit isochrone clouds at every age, and then the one that had the best total cost function evaluation for all the stars within the cluster was picked as the best matching isochrone cloud. And in this case, it resulted in a 185 million year old cluster, which is all things considered pretty similar to literature estimates. But what we see here with the coloring of all the points in this cluster is that the ones with the larger fractional core mass appear to the left side, and that's because these are the younger models. They need to be apparently younger compared to the other stars in this population. And then we can look over here on the right hand side, and the gray distribution here shows again the fractional core mass, the inferred fractional core mass distribution from all the models that we fit to the isochrone cloud over here. And that's compared against the fractional core mass distribution for all of our models fit, assuming just one isochrone that has a minimum amount of mixing. And what we see is that we need a significantly different distribution of fractional core masses within this population to explain the observed spread that we see in this cluster. We did the same thing for a galactic cluster, NGC 884. And again, where the fractional core mass here appears to show that the lighter, the stars with the more massive cores are on the left-hand side because they need to be apparently younger than the stars on the right. And then we compare the fractional core mass distributions over here. And again, we see that compared to the case with little mixing or no mixing, which is denoted in pink, we need a significantly different distribution of fractional core masses. And then in the middle here, we have the correlation, where we have plots trying to show any potential correlation between the rotational characteristics of stars and pulsational characteristics of stars for which we have these measurements. And what we find is that there is in fact no correlation between these either rotational velocity, projected rotational velocity of the stars, or the pulsational characteristics. And this is confirming an earlier result that was shown by Ertz et al. 2014 that looked at something similar for the effects of rotation in abundances in massive stars. And now finally, I'd just like to kind of bring this all together and look at the overall picture of what we have here and kind of go over what we've done. So here in this work, we've developed a flexible framework that allows us to infer the core masses of stars, incorporating potentially independent information in multiple for the components of a multiple system. We've seen that core masses that have been enhanced from internal mixing can in part explain the mass discrepancy as well as the independent phenomenon of the extended main sequence turnoff. And looking to the future, we can kind of see the potential that eclipsing binaries with at least one pulsating component, preferably two, that these offer a window into calibrating stellar structure and evolution models even further. And that is a bit of ongoing research here by several of my colleagues here in Leuven. And then just the last thing that I'll show here is that this work has kind of led to the population of this diagram with for inferred fractional core masses from the binary components that we've had in our sample of the 20 stars earlier, the individual, the G-mode pulsating double line spectroscopic binaries, which we're going to see down here, the clusters shown in gray, as well as combining the results from astroseismic analyses of G-mode pulsating gamma dors and B stars. And this is kind of a way for us to, a new diagnostic for us to try to calibrate stellar structure and evolution models moving forward, where you can just compare the inferred core mass against its expected position according to models that have different amounts of internal mixing at a given age. And just with that, I look forward to the future populating of this diagram, and I will say thank you.
Thank you, Cole, and thank you also for staying exactly within 45 minutes. So great. Well, let us now start the discussion. First, the examination committee will ask questions, and afterwards the public will be given the opportunity to enter the discussion. If someone from the public wants to ask a question, please use the chat, and please do so after the discussion with the jury. You might consider typing it in any text editor and then copy paste it in the chat when I ask you. Okay, let us now introduce the members of the examination committee. Professor Connie Aerts from the Institute of Astronomy of the KU Leuven is the supervisor. Can I ask? Okay. Then there is Dr. Steven Bloemen from Radboud University Nijmegen, the Netherlands, and Dr. Andrew Tkachenko, also from the Institute of Astronomy of the KU Leuven, who are both the co-supervisors. Then we have Professor Hans van Winkel. He is also from the Institute of Astronomy of the KU Leuven. Thomas Kokolios is professor at the Institute for Nuclear and Radiation Physics at KU Leuven. And we have two committee members from the US. We have Professor Andre Pressa from the Villanova University in Pennsylvania. And Jim Fuller is professor at the California Institute of Technology. I am Tim van Ons, I'm the chair of this committee, and I'm from the Royal Observatory of Belgium and from the KU Leuven. The floor is now open for discussion, and I first give the word to Professor Fuller.
Okay, thank you, Cole. Can you hear me? All right, so one of the things you mentioned in your defense is mixing by waves. Can you just describe heuristically how waves might cause mixing inside of a star? Normally we think of them as causing motion back and forth. So how might waves cause mixing, or you could give an example of how they might produce mixing in a different environment.
Okay, so a traveling wave, such as an internal gravity wave, is going to be excited in one place, and then it's going to propagate to another place. And instead of forming a standing wave, it's just going to break in another location and then deposit any material that has been along for the ride there. The angular momentum and the chemicals, it'll deposit in the region where it breaks. An analogy of that in the real world might be, if you take a very simplified analogy, would be if you take a rope and you put back and forth, but it's fixed on one end, so it creates a standing wave coming back to you. Versus if it's open on the other end and you whip the rope, and then you just see the wave stops once it hits the end of the rope.
So maybe you could describe, like, if you picture ocean waves, how ocean waves might produce mixing.
Yes. So if you're standing on the beach, you can imagine that these waves, the waves coming in towards you, when they crash on the beach, it's a very turbulent crash, and you see that my words are failing me, but the water splashes and spreads out, and that could be something analogous as well.
Great. Yeah, I think that's one possibility. Thank you. Should I ask my next question now, or should we move to somebody else?
No, sure, you can ask your question now.
Oh, okay. I also wanted to ask you about one of your findings is that core mass seems to be a better predictor of a star's position on the HR diagram rather than its total mass. Can you maybe describe physically why that might be the case? Why might the star care more about its core mass than its total mass?
Well, that's because the energy in a star is generated in its core. So a more massive core is going to produce very simply produce more energy. You're going to have a higher luminosity coming out of the core, and then so that will equate to an apparently more massive star.
But why does the higher mass core produce more energy?
It will produce more energy because it will produce more energy because it's you have higher temperatures and densities in your core that allow you to do this more rapidly.
Yep. Okay, thank you.
Okay, thank you, Professor Fuller. We then move to Professor Andrei Presa. I give you the word, Andrei.
Thank you. Cole, can you hear me? Great. So this was wonderful, by the way. Thank you for laying it out so clearly. My question is, could you talk a little bit about the time scales in stellar evolution? So you talked mostly about what happens to the masses and so on. I'm curious about the time scales and then the impact of enhanced internal mixing, different types preferably. What is the impact on the time scales of evolution?
So just very schematically, the lifetime of the star on the main sequence is dictated by what is known as the nuclear timescale, and that is going to be for the sun on the order of 10 billion years or so. For more massive stars, that decreases with increasing mass. And then so in the example that I gave at the beginning of the 3 solar mass star, for that'll be a few hundred millions of years for its nuclear timescale, and by allowing for enhanced internal mixing to take place, you're going to give it more fuel, give more hydrogen to be burned in the core, and then in the difference between the models with the least amount of mixing and the most amount of mixing, change the estimates of that by 30%. So the nuclear timescale on the main sequence will be 30% longer in the case of with enhanced internal mixing.
And then the other two timescales, so the pre-main sequence and the post-main sequence?
So we have the timescales, as in the Kelvin-Helmholtz and the dynamical timescale, or?
Yeah, that and the impact of internal mixing. So the free fall timescale first, and then the Kelvin-Helmholtz. What can we expect?
So the free fall timescale is going to be on the order of half an hour or 20 minutes in our sun, and for larger stars, it's going to be on the order of a few hours. It can be on up to the order of several hours, and mixing is going to be either it's going to be much slower in most cases in this, except for convection. Convection is assumed to be a very rapid, turbulent process, and I'm not entirely sure where the in certain stars, let's say, the convective timescale might be longer than the dynamical timescale, or vice versa, and I'm not entirely sure where that turnover happens. But then for the thermal timescale, this refers to the how long a star requires to readjust to some perturbation to the thermal structure of the star, and that'll be a few hundreds of thousands to millions of years, depending on the star that you have. Or tens of millions of years even. And mixing will be more, the mixing that we're looking at will be more rapid than that, but likely in most cases less rapid than the dynamical timescale for these stars.
Okay, just watch out for the free fall timescale. If you're talking about pre-main sequence, it's much longer than the numbers that you were quoting. Okay, so I'll follow up on what Jim asked earlier about the core mass being the only influential parameter. So my question is, when you build your mixing model of the three components, what simplifications would you say that you had to make are most influential? Now, you clearly demonstrated that the mechanism itself does not play a major role, rather than the presence of mixing per se. But for the future work, can you think of any way to revise that model, or do you believe that you'll always be limited by the observations?
So in the case of the envelope mixing that we took to be the profile from generated by internal gravity waves, that was produced or deduced from 3D hydrodynamical simulations. And then we just averaged over the average mixing profile in the entire star that has been in use by these waves, and then scaled it down. That was first implemented by Peterson et al. 2018. And that the limit there is, I guess, how you conduct your averaging down from your hydrodynamical simulations, which are three-dimensional, to a one-dimensional stellar evolution code. But I would say that the more important problem comes in the treatment of convection in 1D stellar evolution codes, and one-dimensional stellar evolution codes, because convection is a turbulent three-dimensional process. And then the way that we describe it in our stellar evolution models completely neglects the mixing that might happen at a convective boundary. It just assumes that any convective material you have comes to the boundary and then stops. And that's why we were incentivized to use something like the convective overshooting model, which describes what happens when a convective blob doesn't stop at the boundary, but instead shoots past it a little bit and then mixes with the layer around it. So really, we need more accurate descriptions of convection, I would say, but that is, with current computing power, a very difficult process, because stellar modeling is a balancing act between making these simplifications so you can actually run a stellar evolution model, not only just for one time step, but for over several time steps for millions of years for the models that we have, and still wanting to be accurate. And mixing link theory, which describes convection, is one of these places that we have this problem.
Okay, and very briefly, I'll ask the last question. Could you talk about some sources of systematics that are present when you're computing isochrone clouds, and what the impact of those systematics may be on the solutions that you've presented?
Systematics. So obviously, I would say the largest systematic is all the uncertainties that go into the stellar models themselves. The stellar models, although incredibly complex, they still have a lot of knobs and buttons that you can turn and press. There are so many bells and whistles that you have to make some choices. And now you can try your best to physically motivate your choices for some of these things, such as the opacities, the tables that you use to compute your opacities in your stellar models, your equation of state, your chemical, your nuclear reaction network. Sorry. All of these things are things that we would just assume to be fixed in our stellar models. And then, of course, changing these can have quite drastic effects. So as long as you, for a given population of studies or results, you say that you're using the same things across the board, you know that the systematics are the same. And that's kind of the best you can do in this case. Try to control the systematics.
Thank you.
Okay, thank you. I now give the word to Professor Thomas Kokolios.
Hi, Cole. Good afternoon. Thank you for your presentation and this definitely extremely interesting work. I've had a lot of fun reading it and discovering myself a lot about it. I actually have a continuation on the continuation, so I guess there's a red line through our questioning. I want to bring it to the very general type of question. That is, with respect to your field, where do you think the main bottleneck is at the moment? The way you worked, you have your model, you make your computation, you challenge against observation. So which of those three is currently limiting you? Where do you think there should be most investment done? Because what we haven't said yet is the observation aspect, but you did say at the end, I'd like to have more points in this plot, and I'd like to build that up further. So where do you think is your main limitation at this stage?
I would say that it is exactly at the sample size. There's a tremendous amount of work that goes into the observational characterization of any of these stars individually or in multiple systems, and that takes a majority of the time. So currently, there's something like the NASA's TESS Transiting Exoplanet Survey satellite, I believe, which is painting the sky. It's going to cover about 85% of the sky and give us coverage of millions and millions of objects. And there are other surveys, future surveys, which will do the same. So first, we have to identify the interesting targets. And then we have to find another way of doing the analysis kind of quickly, because I said we're taking it for granted earlier. And then finally, the modeling that I discussed is actually, it's still fairly time consuming. And there's been some great work by my colleague, Dr. Michael Pellison, who recently defended her PhD, where she has taken the step to modeling these stars not with individual grids of stellar models, but with statistical models, statistical representations of models. And a similar thing has been done for lower mass stars, where you can, instead of taking weeks or months to do a model, in your modeling efforts, you can do this in seconds or minutes. So it's kind of, you get past one bottleneck where you have, now we have a ton of stars to look at, but then you have to all right, now we have to actually analyze all those stars. Then once you get there, you still have the last bottleneck of doing the analysis, which can take a long time in and of itself. And then finally, you can come over here and look at the whole picture.
Okay, yeah, it sounds reasonable, but also exciting as a sign of future prospects.
Absolutely.
But in spite of the limited statistics that you have, the limited amount of stars you have to work with, there was something quite interesting you said at the end when you said that the enhanced mixing was partially solving the mass discrepancy problem, in the sense that you could see there was actually a subset that gave you a perfect no discrepancy, so where it showed clearly worked. And then there was another subset that had an also very clear single trend, whereas your original plot where you compare solution 1 and 2, you do show a line, but it's, to me, somewhat reminiscent of Hubble's law, where you get a cloud of points and a point very far and you say this is a line. And then suddenly you have those two sort of groups that really stretch off from each other, and that's, in one sense, very much more convincing. But then my immediate question is, what are those two subgroups? Did you see any correlations within each of these groups that would highlight to maybe where the rest of the information, where the rest of this mass discrepancy may come from?
So there's two places that I think we should start our investigation with that. First, observationally, in the binary analysis, where you get the parameters of the stars themselves, you have to worry, you have to determine the parameters. And in the case of, you saw that these were the more evolved stars. So they were more to the righter side, the rightmost side of the plot, and those are the more evolved stars. They're generally going to have a less dense atmosphere. And then there's a problem with the determination of parameters from atmosphere models in less dense, in these less dense atmosphere models, where you have some wiggle room, let's say. And additionally, you have the problem of the inclusion of certain microphysics in your atmosphere models that will then change your solution. So you can kind of move your solution by 1,000 Kelvin, let's say. More specifically, you can move it cooler by about 1,000 Kelvin, depending on if you include some of these extra microphysics, or how you set the values for them in the atmosphere modeling. And then the second one is that we restricted the mixing range, the range of mixing efficiencies in our models to those that have so far been found by astroseismic analysis. That's not to say that future astroseismic analysis won't allow for a wider range of mixing efficiencies that we can then include. We could, if we were to repeat this, maybe these are just systems that need more mixing to explain their observations, and that could be one more potential source of this.
Okay, yeah, sounds even like almost a to-do list of things to explore. One final question. When you described the binary systems, you brought some assumptions that came along with them, or very good starting point, I should say, rather than assumption, which is same age, chemical composition, and that we can extract the masses, the radii, very accurately to a 1% precision. All of those are individual properties. So you can get those information for each star. How relevant is the relative properties of your binary system, or even in a cluster case, such as the distance to one another, their periodicity in their relative motion, and that sort of things? Can that have any influence on their evolution? So I don't mean on the observation, right? Because you use all those parameters as part of helping you determine those properties. But can it also change the evolution as a whole and what it can become beyond their inner properties?
Absolutely. And in what we've done in this work is we've taken all the benefits of binary stars and handpicked systems that fall within the safe realm of this. But in general, binary stars open up the possibility for a very complex change in their evolution, where sometimes if the stars, or when the stars are close enough to one another, when one star begins to evolve, it will transfer mass onto the other star. So this one will become less massive, this one will become more massive. The two stars can even spiral in on one another, and stripping the envelope off of one of them. You can have a whole wide range of really exotic physics that come out of binary interactions, not but for just binary systems, but triple systems, and then scaled all the way up to multiple systems, or you could even clusters where it's thought that there are merger events that happen quite regularly. And then a lot of these are kind of thought to be responsible for some of the more exotic objects that we see in our universe, such as Wolf-Rayet stars, which are essentially the stripped cores of very massive stars, whether it's through wind mass loss or through binary interaction is ongoing research.
Okay, so the model as you've described them here actually is not one size fits all. It is for those very specific binaries that are behaved enough that you can work with them.
They're behaved enough, and that was part of the reason that we chose them. That they fall within this safe set of assumptions, that they haven't interacted yet, so we know that they haven't deviated from what would otherwise be a normal single star evolution at the moment. That's not to say that they definitely won't in the future, though.
Okay, thank you very much, Paul. That was all for me.
Thank you. I now invite Professor Hans van Winkel to ask his questions.
Hello, Cole. First of all, I would like to congratulate you on your work and your presentation. The work is impressive, not only in the nice results, but also in the volume, the total volume of work that you've done and the different aspects that come together. That's very nice to see, and it was very nice to read as well. I do have a question, though, or several questions, and I'd like to start with something that you not really touched upon in your talk. It's about tidally perturbed oscillations.
Yeah.
Because I remember that you were very happy with finding U-GRU, I think.
Yeah.
One is an example where you had that tidally perturbed oscillations. I see. But to me, it's not the question is not about finding them in U-GRUs. The question is more, why only there? I mean, because binarity is very widespread phenomena. It's whatever, 50, 60, 70% of the stars are in binaries, especially at higher mass star. And yet it's not very predominant, the tidally perturbed oscillation. So can you frame that a bit? Why is it so unique, or why is it so special? And why don't we find it everywhere?
So in the case of the phenomenon that we see in this particular system, U-GRU, it seems like it's a very low amplitude signal. And we haven't seen this exact signal, or at the moment, we're not sure if we've seen this exact signal elsewhere as well. So we don't, I would say that we don't have much predictive power in saying that we should see it in other systems. It's very likely that it is also apparent in other systems. It's just, it could be in one of the potential things that we're seeing is that it could be due to the relative light ratios at a phase of the orbit that we're seeing. So this phenomenon might only be observed when the relative light ratio of the more bright component in one star decreases during eclipse, and then you see as a fraction of the total light, the other star gets a higher fraction, and then this low amplitude signal now gets boosted. That's one potential candidate.
But then it's present in many stars, but you don't see it.
Potentially, again,
Yeah.
it's hard to make a statement on that because we're still struggling to understand just quite what that phenomenon is. It could also be that I know one theory that's favored by some people on this committee is that it's the result of geometric cancellation. So as you have a pulsating star, and it's pulsating, and as you have your other star eclipsing it, you get it's how do I say this? You block out part of the light of the pulsating star, which changes the apparent amplitude of that pulsation, or potentially it could make some pulsations visible, because for higher degree pulsations, they'll cancel out over the integrated surface of your disk. So now if you block part of the disk, all of a sudden, or you asymmetrically block part of your disk, you can all of a sudden see these pulsations. And then that could perhaps be a part of it, but you would need that exact degree mode to be a high degree pulsation mode to be active in that star, such that when it is blocked, you would see it. And again, if that's not a high enough amplitude pulsation, you're not going to see it anyway. So this could still be happening. It's just that our instruments aren't precise enough.
But that also means that it's only seen in eclipsing binaries. So it's not. It's a geometric effect, not a physical, or not an intrinsic physical effect.
If that is the interpretation, then yes, that would only be seen in eclipsing binaries, or in a case where you have something that partially obscures your disk.
Okay.
Periodically.
Okay. Thank you. Then I have another question. Also, towards the end of your thesis, you start a few items with the title "Towards Precise Modeling." So, towards precise modeling of pulsating stars in binaries is one of them, and towards a generalized sample of ensemble modeling and so on. But so, to me, I did not quite understand what is missing to do this. I mean, so what is on the road next to work? Because in my opinion, you did already do quite some precise modeling. So what do you mean towards?
In particular, what I mean for towards in the case of the individual cases, yes. I've looked at a global astroseismic diagnostic as opposed to the individual pulsation periods yes. For the in the pulsating star, and those are far more stringent when it comes to the constraints they place on stellar models. And then so part of the problem with this is that we're having just a really hard time finding good examples of eclipsing binaries. So where you can get the precise masses and radii that also have, a lot of stars have G-mode pulse. There are a lot of binaries that have G-mode pulsations, but in particular, we're looking for a pattern of pulsations that allow us to make a mode identification. And then that is where we get the strong modeling power. There's a bunch of people here on Connie's team that can tell you that is a very difficult thing to do. And for instance, Sanjay Sekharan has looked through 70 or so eclipsing binaries with G-mode pulsations, and I think he found 2 promising candidates to do that. So what he can end up doing is taking the methodology that we've developed here for the Isochrone clouds with the global astroseismic condition or diagnostic, and it's directly applicable to that case, but instead of the global diagnostic, a global astroseismic diagnostic, he'll use the individual periods with this pattern. It's just that it's been a very hard effort and a lot of work to try to identify specifically those systems where that can work.
So it's really a sample selection.
In that case, yeah, we're just not finding many eclipsing binaries that have these patterns.
Okay, thank you.
Thank you. And we will now move to the co-supervisors. So the first one is Dr. Stephen Bloemen. Do you have questions?
Yes, I have one more question. Thank you, Paul, for the very nice presentation. And today, you're getting close to the end of your defense, so I think it is fitting to ask you a question about the very final sentence of your thesis. And you don't have to look it up, but it's about the isochrone clouds and the fact that stars that have very similar identical initial conditions, mass and metallicity, can end up having very different core masses due to different amounts of internal mixing. And at the end of your thesis, you conclude that which specific mechanisms are at work that create this different internal mixing is still a task for future investigation. So can you give a quick overview of what you think those processes might be? And then also, how do we go about investigating which ones are at work? Because you say it's important to get large generalized samples of stars, and that future missions like Plato and also the current TESS mission may produce the data that you need to do this. But what would you then look for? Which are the stars you would study first, and what are you looking for to solve this issue?
So for the first part of that, why stars with similar initial conditions might end up having different core masses. One thing that we just more or less ignored in this work, but kind of tried to account for in our mixing profiles by saying that all mixing can be used as a proxy for other mixing, or any one mechanism can be used as a proxy for others, is rotation. All stars rotate. They're not all going to be rotating at the same rate, obviously. And then so that will lead to differences. So two stars that are otherwise born at the same mass but have different rotation rates will obviously have different amounts of internal mixing based on those rotation rates. That is one aspect of it. Another aspect could be pulsational mixing, which is something that's still not entirely very well understood to the best of my knowledge. And then that comes down to mode selection. Why do some stars pulsate in some modes and then others pulsate in entirely different modes? And then so the mixing induced by these different ones will, these different stars that have different modes could propagate to different amounts of internal mixing as well. So things such as that. I guess for what we would look for, the targets that we would look for in the future to help us try to estimate this more is I would personally like to find an eclipsing binary with two slowly rotating stars, so that we know that we can kind of say that rotation is a less big player, that are undergoing apsidal motion, so that we have multiple ways, and also pulsating, obviously, because then we have three different ways to solve the core mass in this case, and you can solve it individually and then put it all together, and then these also give you different ideas of how you can apply the information at different levels to see what information is affecting your solution, and maybe you can say something on the different mechanisms at that point.
Okay, thank you.
Okay, I now give the word to the other co-supervisor, Dr. Andrew Tsikacheko.
Yeah, thank you. Yeah, cool. Congratulations. Yeah, excellent research. Very good results. Yeah, so excellent presentation. I'm very happy with it. So, and I will actually skip the questions because I have all the opportunities to ask questions, and God knows how much time we actually spend discussing all your research. Yeah, and I'm really looking forward to continue this kind of collaboration in the future.
Thank you, me as well.
Does the supervisor, Professor Corey Arts, wants to ask a question now?
Well, I asked many questions during many years, up and including until last Tuesday. So I'm gonna shut up for a while now and take the floor a little bit later.
Okay, thank you. As the chair of this committee, I was not planning to ask a question, but in the beginning, in one of your first slides, you said that G modes show some similarity to waves traveling at the surface of a pond. And I tend to agree with that, but I have a maybe basic, maybe nasty question. That is, what are then the differences between the G modes and waves traveling at the surface of a pond? I think you're muted, or I have an internet connection problem.
Sorry, that was me. The waves at the surface of the pond are propagating radially outwards on a flat surface at what is assumed to be an infinite depth.
Sorry, I was giving a sign to someone doing a delivery at my house.
And the waves are propagating on a surface below which you assume to have, you can approximate to have a fairly infinite depth in a lot of cases. And you're propagating in water, whereas which is a liquid, whereas in a star you have a three-dimensional medium, and your waves are propagating in mostly well-behaved but very hot gas.
Yeah. Did you mention buoyancy?
Yeah. Oh, sorry. I might have mentioned it on the
during your presentation, so I think that's an essential difference, of course.
Yes.
which is in G modes in internal gravity waves, but not in the surface gravity waves.
Yes, sorry.
Okay, let's move on to questions from the public. Are there any questions from the public? Maybe the secretary can help me there.
Apparently, there are no questions from the public. There is one very interesting comment that I will display now. So it's on the screen. That gives us a minute of time, well, the audience a minute of time to actually type in their questions if they have any.
Okay. So we will see for a minute or so if some questions from the public pop up. If you want to ask a question, maybe you just type in that you want to ask a question and then we can wait a little bit for it. Otherwise, we will move on with the session. So please do so within a few seconds if you want to ask a question in the chat. I can answer that question for the moment negatively. You will have to wait. I see a question here that can we call him Dr. Johnston? Okay, I propose that we move on now, and the jury will now have a deliberation in private, and we will come back to this place soon. So we will hear you soon. Ladies and gentlemen, dear colleagues, I will now proclaim the result of the deliberation by the examination jury appointed for the doctoral degree in science, astronomy and astrophysics. Mr. Cole Johnston has presented to the faculty his PhD thesis on the topic Interior Modeling of Massive Stars in Multiple Systems, in partial fulfillment of the requirements for the PhD in science, astronomy and astrophysics, and he has defended his thesis in a public session before the examination committee. The examination committee has determined that all requirements concerning the granting of the doctoral degree that are prescribed by the law and by the university regulations have been met. Therefore, on behalf of the Rector of KU Leuven, I confer upon Mr. Cole Johnston the degree of Doctor in Science, Astronomy and Astrophysics. Congratulations, Cole. Well done. Okay, I hereby formally close the session, but the session doesn't really end. I now pass the word to the supervisor, Professor Connie Adamson.
Yes, thank you. Can you all hear me? You should, huh? I hope. Well, Dr. Cole, congratulations. There was a question in the chat. Yes, now he's Dr. Cole. And so isn't that nice? My sincere congratulations with this successful PhD defense, an online defense, quite original. And I'd like to welcome you to the club of doctors in science. At this occasion, I would like to, it's a milestone in your life for sure. And so I'd like to reflect a bit on the road that you took to get here. For those unaware in the audience over there, Cole and I share quite some commonalities. We love observing. That's one thing. We are fond of jogging. And Cole's speed is about a factor 2 higher than mine in this activity. We love traveling, right? Both of us, and we kind of miss it for the time being, but we'll overcome that. We tend to get lost. But so far, I've never ended up on the wrong island, in contrast to Cole. Yeah, so even doctors in science tend to make that happen. We also have a love for eating pizza. That's also a commonality, I would say. And last but not least, we both love New York City, right? And in fact, I keep on wondering, how can someone living so close to New York City can prefer living close to Leuven? That remains a mystery to me. But anyway, if you're close to the city as your hometown and still prefer it here, that must mean that there's another love we share. And that love is called astroseismology. And I think that's what brought you here. So perhaps it's even fair to say, and I'm risking some criticism of the New Yorkers now, but even the city is perhaps not as able as we are here in the small town of Leuven to do astroseismology. And in addition to that, not every food shop in New York City sells speculoos. That's another reason, right? Leuven is special for quite some people on the e-gathering here today, and I'd like to go to your bachelor supervisor and jury member, Andre Brisa, because he also has something special with Leuven. He came and visited here and discovered the star of his life, meanwhile his wife, and grabbed her from here, right? And so I think that's a connection. Surely, Andre, you have had a great time here in Leuven. I'm very grateful when you were here and multiple times, but also for having invited my PhD students to come over to Villanova. These were Pieter de Grote and Steven Bloemen, who we heard today. And I think you taught them everything about binaries in Villanova, but they sort of sparked Cole's interest in astroseismology. A along with Ehsan Moraveci, who was there at that time, also working with you. And I know this had a major impact on Cole's dream. Cole got a dream and made a plan, and you helped it realize. So I think that Andre is very happy for having picked up Kelly here somehow. I'm very happy for you having sent an excellent bachelor student to Leuven. So I call this a win-win, right? And as it happens, actually, both Cole and Ehsan ended up in Leuven. And both of them like it here so much that they are not in a hurry up to this present day to go back to their origins. So I take it as a compliment. I'm not sure if Ehsan is online, but anyway, I also like to mention him because he played also a good role in Cole's story, let's say. Cole, you are my first American PhD student. That's a primer. Yeah? You came here on a semester first, after a detour via Don Kurtz, who is Kelly's supervisor, while you were still a bachelor student. And you got hooked on binary astroseismology here, also thanks to Paul Beck, who was my former Viennese PhD student, also online, I hope, because Paul sparked your interest even more into this topic, and it was clear that you actually wanted to go back home. You had to graduate as a bachelor, but you wanted to come back as well. So we send you off to the US again, but keeping in mind that you wanted to come back. And you actually managed to do that on your own funds. And I'd like to stress that because you got yourself one of these highly prestigious Belgian-American educational foundation scholarships that allowed you to study here in your master. And that was done under the co-supervision by Steven Bloemen, remember? So I kind of think that like all the people that I named by now, you should make a TV story out of their stories, because that would be a good series. Yeah. And when you were here, graduated as a master, you wanted to start a PhD, you were already, and then came in this fresh Danish master's graduated student to do that along with you. So I'm actually very happy that Mai defended last week, you did it today, and that is a real pleasure. I thought you were the optimal PhD doublet, as I tend to call you, for my ERC MAMC grant. So nothing can stop us from achieving that. You graduated these 2 weeks, not even Corona. And so I consider that a big success. What Corona did manage to screw up, and I'm really a bit sad about that, but anyway, we have to live with it, is that your family was planning to visit you here and to celebrate with you here today. So I'm now going to have to address the Johnston family over the internet. And I would like to say that I would like to congratulate also the family of Cole, because we are all very proud of Dr. Cole now. I'm sure you are too, as parents, as brother, as sister, as uncle, and as American friends who are listening in. Thank you so much for having supported Cole in these times, in this task of today, but above all, in the past years. And so it's planned that we shall hold a big ceremony. That was in our plan. I have something with acronyms, as my students know. I even already had an acronym for Cole's festivities here. The BAF, I call it, Belgian American Eat and Drink Festivity. That was what I had foreseen with your family, with lots of Belgian beers. I suggest that we keep this plan. It has just been postponed a little bit into the hopefully not too distant future, but we definitely have to celebrate that in other times, let's say, that you are now a doctor in science. Johnston family, you have sent me a very polite, motivated, and nice young man. We are all grateful that you allowed him to leave New York to be in Leuven for these past years. I don't know how Cole behaves when he's among his family, but to me, he has never ever complained. He just doesn't complain. Maybe that's a little different as a brother or a sister, perhaps. I can't hear them now, so I'm curious to find out later. And if I ever get the opportunity also to be close to New York again, we'll visit, but we'll meet again and we'll get you here at some point. Cole's positive mindset, his kindness, and his passion make him very pleasant to work with. It's above all your achievement because you raised him as a kid. And these values were given to him by you. So I'm very thankful for that. I think you should be very proud. Cole is very often chosen as a student tutor in this institute, but also as a collaborator worldwide. And I think this has everything to do with his knowledge, his experience, but certainly also with his personality. He's also very socially engaged and always around to help others. And we value those aspects as well. It's just not only about science. Cole is always prepared to help with the initiatives of the institutes. He keeps track of a curve, I should say. Nowadays, a lot of people keep track of curves. But in Cole's case, it's not the COVID-19 curve, it's another curve. And I'm not sure if he knows what I'm aiming at, but Cole keeps track of the speculoos consumption curve of this institute. And so he has no intention whatsoever to flatten it. And so I guess he will continue to do that. I'd also like to take this opportunity to thank Andrew Kachenko as your co-supervisor. I'm sure you will agree with me, Cole, that you learned an awful lot of things from Andrew. And among these many things, there are two that I definitely could not have been able to teach you as well as Andrew. The first one is a no-brainer. He taught you how to play basketball. I can't do that. But he also told you or inspired you on how to do binary astroseismology in a way that he can do better than I can do it, in fact. And so in his usual Andrew, quiet, very to the point style, I would like to quote him on something he said while we were deliberating among your jury members after your internal exam. Andrew said, well, I see Cole more as a collaborator than as a PhD student. And I think that summarizes it all. This is how your jury sees you. We see future potential in you. We know you have become an independent astrophysicist. And we have given you a lot of luggage now to move on and to continue your road in academia. I am not so hesitant of sending you off, even though you tend to get lost. But I'm sure that on the next road that you're continuing now, your other co-supervisor is there to prevent that you would get lost. So thank you also, Steven, for your role in Cole's co-supervision so far at his master's thesis level. The past few months, this was a bit at a loose tie, let's say, because Cole is now moving ahead to Radboud University, and you have facilitated his integration there. When Cole was actually already doing some of my lecturing there recently, and I should thank Cole for dragging along a good Nijmegen student here, who is now a PhD student here. So we have this very pleasant road, Leuven-Nijmegen, that we, of course, have been improving all the time. And I'm happy to send you off on that road now to work on BlackGem, where you will have the opportunity to do science exploitation on stellar variability. I'm sure you will like that. So, Dr. Cole, we are all very proud of you today. Happy that you are continuing your scientific career in this part of the world even, that we call Benelux, right? You want to hang on here for a little while. I'm sending you off to Radboud. I sent off Steven many years ago to Radboud, and he didn't come back. So at some, that's a statement, right? It's going to be fun over there. And I should also say that even Steven grabbed his wife here in Leuven, so that seems to be a constant in this story. Valentina, who was here when you were already here, is now in fact over there, and she will be very useful for you because she has taken up a job as project coordinator. So she's the Nijmegen Clio, if you like. And so I look forward to visiting you. I also plan to come back there frequently because, of course, I want to see the Black Jam results. And so it's a fascinating new instrument. I'm sure you will like it. I am also sure you want to go and use it in Chile at one point in the not too distant future when we can travel again. And then move back actually to your first love topic of your master thesis, pulsations in compact binaries. That should be great fun. But for now, I think I said enough. I would like to sort of allow you to relax into a little celebration here locally. But before I do so, I would still want to ask again for the audience to join me in a big round of applause of our fabulous new doctor. Congratulations, Cole.
Way to go, Cole.
And now you can talk, Cole, if you like.
Yes. Thank you, everyone, so very much. I think most people will agree that it's not very often that I am at a loss for words. But before I say anything else, I would like to clarify the point about me getting lost. For those of you who don't know, there's a point where I, at one point, flew to the wrong island while trying to get to La Palma, and entirely my fault, but I would like to point out that airport codes can occasionally be tricky, and there is only about an hour worth of observing time that wasn't really lost, thanks to the amazing technical staff and science support team at the Mercator Telescope, as well as Carlos, the taxi driver, who waited to drive me up to the observatory. So that is just to say that specifically in that moment, and more generally, this entire thing that I've done has been with the help of just so many people. And I can't say thank you enough to everyone who was involved, starting with, of course, my family back home who have put up with me and my droning on about science and binary stars and pulsating stars and binaries for years. And I think, to their credit, I'll say that they have given me a few ideas over the years with some of the questions that they've asked. So thank you for that. And my friends as well. So they've done an amazing job of just always finding the right words to say when I might need an extra little bit of help in anything that I'm doing, whether it be leaving the city and coming over to Belgium, or even just the day-to-day things. But it's indeed true that when I came here, even the first time, I fell in love with the culture, the city, the beer, and the fries. And so I've made a number of friends here in Leuven while partaking in the beer and fries. And it's not something that I want to leave anytime soon, as you have mentioned. So New York has a lot of great things. They do have pizza, and I will never be able to move past that. But Belgium has the fries and the chocolate and the beer, and what more can you ask for in life? But I do want to take just one moment to say thank you to you, Connie, for taking a chance on me as a bachelor student, allowing me to come over and accepting the word of Andre, being like, oh yeah, it'll work out. We'll send him over. But I think on Andre's half, he benefited because when I came back to Villanova after being here for a little while, he made fun of me endlessly for how I came back more cultured than ever. And in particular on the way that I decided to start wearing my scarf like a European. So Andre benefited from this exchange as well. But then you were very kind and welcoming to me when I said that I would like to come back, and aided in the application for the BAEF and all of these things. And just the very non-linear path that I took to get here wouldn't have been the same without your guidance and that of most other people in this institute as well. I've said a lot of times that family are the friends that you choose, and I don't think I entirely got that right. Or, sorry, friends are the family that you choose. There we go. I still don't think that I got that right the second time even. I think it's more that friends are the family that choose you. And to that extent, I'm very happy to say that I have an amazing family here in Leuven that I don't want to leave anytime soon. So with that, I'll say thank you.
Bubbles call. Bye, everyone.
Bye-bye, everybody.